Okay, continuing on with examples from class 14. Here is an example from Munson's fluid mechanics. We have another sprinkler, and there's a couple differences between this and the previous example. Water enters a rotating lawn sprinkler through its base with a steady rate of 1,000 milliliters, or 1 liter per second, as sketched here. The exit area of both of the two nozzles are 30 millimeters squared, and the flow leaving each nozzle is in the tangential direction. The radius from the axis of rotation is 200 millimeters, right there, so 0.2 meters. So we want to determine the resisting torque required to hold the sprinkler head stationary. And then we also want to determine the resisting torque associated with the sprinkler rotating at a constant 500 revolutions per minute. It would be behoove us when that's happening to also figure out what the power is at that state. And then we also want to see determine the speed of the sprinkler if no resisting torque is applied. So there's a couple differences between the previous example and this. So let me start out with finding the mass flow through. Let's go through each nozzle, right? So the individual nozzles. I didn't mean to write that right there. Let's go. Let's get our heads in the game here. What that is, the NOS. All right, so it's going to be the density times the volumetric flow divided by 2, right? Because there's 2 nozzles. So 999 kilograms per cubic meter. We have 1 liter per second, and a liter is 1,000th of a 1/1000th of a cubic meter. So that right there is going to give us close to 0.5. I'll keep the numbers here. 0.4995 kilograms per second, right? So, because this right here is 1 liter per second. It's 1/1000th of a cubic meter per second, and times the density right there. Look at the velocity of the jet. Right, and so the jet is going to be moving. And by the way, as designated here from their convention, that's going to be a capital W. So I'll go ahead here, and they're calling that it's coming outward. So 2 is going to be that W right there, and that's going to be the volumetric flow rate divided by 2 divided by the area of the nozzle. So that's going to be 1/1000th divided by 2. So that's the flow rate. And then the area, they told us it was 30 millimeters squared. So a millimeter is 1,000th, and they're squared. So we're divide that by 1e to the 6, right? And what that turns out to be is 16.67 meters per second. I guess I'll leave it right there. So this is the speed of the jet, right? So we're going to hold it stationary. So I'm going to draw this FBD. Let's see, I'll draw it like that. And so here's our FBD. And we're going to be having our MD, our momentum diagram over here. I guess I'll erase that stuff in the middle there. Okay. And the only forces that we're going to have over here, we're going to hold this torque, and I'm going to put a T in that direction right here. And we're going to have an M dot and a V. I guess we'll call it, that's actually going to be the stuff coming out. So that's actually going to be the W2 in this first part of the problem. So M dot V. And I'm going to leave it without a subscript because I might want to refer back to this diagram. So the equation that we're going to use here is the out R M dot V minus the summation of the in of R M dot V. Got to be careful what velocities we use here, and we have to think our way through it when we do it. All right. So in this one, this is the one to stop it, right? The torque to hold this thing in place is going to be, I'm going to keep this as positive because it's counterclockwise. I'm considering positive. I drew it as positive, but I don't know what direction is actually going to be. And the outlet right here, we note that this is going to be in the clockwise direction. So its sign is not only dependent on whether it's in and out, but it's also onto what direction that it goes. And so that's going to end up being -2 times R and m dot. And in this case, it's going to be the velocity of the jet, right? Because that's what's actually coming out. And so we have -2 times the distance is 0.2. It's the radius. They told us it was the radius. And the mass flow 0.4995, and our velocity 6.67. So the torque to hold this thing in place is going to be a -3.330 Newton meters, or 3.33 Newton meters clockwise, right? So that's going to be like answer to the A part right there. Now for part B, we're gonna need to find what the velocity of this thing is going to be. Now we note that it's rotating in that direction, so they're using the variable u to represent the motion of the nozzle, right? So they're saying u2, and I might call this the velocity of the nozzle, and that's going to be omega times r. And so I might want to find omega separately. I didn't do that in here. So maybe I want to go ahead and turn maybe up here somewhere. Omega is equal to 500 revolutions per second. So it's going to be times 2 pi and divided by 60. So that ends up, this is kind of messy. I wish you wouldn't be messy, so I shouldn't be messy, right? So that should be 52.36 radians per second. So here, I'll put a thought cloud around it to kind of separate the thing out. So here we go, 52.36 radians per second times the radius of 0.2 means that this thing is traveling at 10.47 meters per second. And therefore, what they're referring to as my V theta 2, right? And what they mean is this is the tangential velocity of the thing. So we can go V, they're calling it theta 2. We can say the velocity, the tangential velocity, it's the actual velocity, is going to be the V jet minus the motion, the V nos. All right, I want to use mine, V nos. You'll see in the next problem where we're going to use triangles, right? But these all line up with each other, so the vector math of that isn't anything but subtraction right here. So 16.67 minus 10.47. So we're going to use 6.198 meters per second. So if we use that same equation we had up above, now we're going to have or just maybe this equation right here. We're going to have the torque of the outlet right here. And let me go 500. I'll just give it, maybe I'll write this as a stop. This is the torque to stop. The torque at 500 RPM is going to be our negative, but there's two of them. I forgot, 2. Right? So we're going to go 2. 2 times radius 0.2. Mass flow is going to be 0.4995, but now the speed to use is 6.198. So what I'm left with is a negative 1.238 Newton meters, or 1.2,4 Newton meters clockwise, right? And that's really the answer to part B. I think it's worthwhile to figure out what the power is, and the power is going to be the torque times the angular velocity. So that's going to be 1.238 Newton meters times our 52.36 radians per second, and we're left with 64.84, and that's Newton meters per second, therefore it's a watt. And then part C, we want to determine the speed of the sprinkler if no resisting torque is applied. Well, let's go ahead. So we're going to stick in 0 for right here. But now we want to go back a little bit and say, well, what we really want to use here is not the velocity of the jet. So that was only specific to the stop, because it was, well, we want the relative velocity, right? So we're going to see, so the idea here is now we're going to have like maybe T is going to be equal to -2 times R m dot. And so we go V theta 2, or the tangential one. So this would be -2 R m dot. And let's go V jet times the velocity of the minus the velocity of the nozzle, which is R omega. So we'll be able to find out what omega is, because we're going to set that equal to 0. And then this isn't going to matter, that these run right here, because they're all multiplied by the thing. But the only thing that's really going to matter is that we're going to take that V jet, which we knew was 16.67, minus the 0.2, and then we'll be able to find omega. So we end up finding omega is equal to, so that's going to be 16.67 divided by 0.2, right? Because the stuff inside here has to equal 0, and these don't matter right there. So what we find is that we get 83.35 radians per second. So the speed of this, we might want to multiply by 60 and divide by 2 pi to get it into revolutions per second. We get 796 RPM. So that's going to be the answer to part C. Interesting to now take a step back and compare what we had here, right? So here's, if you hold it in place, we get the torque. Here is the torque at 300, and here is, if we just let it go and there is no torque, we have almost 800 RPM. So stationary, 500 RPM, nearly 800 RPM. It doesn't produce any power here. It doesn't produce any power here, because it doesn't have any angular velocity, so that can't be any power. And it doesn't have any torque, so that can't be any power. But right here, we are able to generate power. So it's really sort of like, we can think of it as a governor is the thing that kind of that controls the speed of in many instances of a piece of equipment. And will be related between this torque and RPM, depending on the amount of available energy right in there. So there you go. I think it's a pretty good problem. I think it really complements the previous example, because now we are trying to get a better feel for this real piece of equipment situation. So we'll continue with another example, and next time we'll use velocity triangles, because we'll have a different velocity direction in the outlet.